what do you mean chemistry for biology? I sign up for biology. I don't want to learn no chemistry. Well, chemistry and biology are very close together, and you do need to have some knowledge of chemistry to understand biology. I'm not just telling you something the book says. I'm talking from experience. I was an undergraduate. I used to go to my professor and ask a question. Why does the NADPH producing glycolysis, why it can't cross the membrane into the mitochondria? Why? And the professor looked at me and said, that's chemistry, don't worry about it. Every time I asked a question, that was the answer I got. And not from one professor, several. That's chemistry, don't worry about it. Well, maybe it's chemistry, but they didn't answer my question. So when I went to graduate school, I decided to get a master's in chemistry. Then I went back to my first love, biology. And now I can understand biology much better. You do need chemistry if you're going to learn biology. So let's look at some very basic chemistry. I promise. We're going to cover in one lecture 2 semesters of chemistry. So you realize it's going to be very light. Chemistry is going to be the study of matter. And what is matter? Anything that takes up a space and has mass. Everybody's familiar with the 3 states of matter: solid, liquid, and gas. Nothing new in here. All matter is made up of elements, and an element is a substance that cannot be broken down into simpler substances by ordinary chemical means. The typical element is the atom. Okay, so an atom is the smallest unit of matter. You can break an atom. We know it's made up of subatomic particles, but then you don't have the element. Okay? So we know that atoms are composed of subatomic particles. You have protons that have a positive charge, and they have some mass. It's not a whole lot of mass, but they do have some mass. Neutrons are neutral. They don't have a charge, but they have mass. And the electrons, as you said in here, negative charge. I missed up when I was typing. And the important thing about electrons, they're so small that we're going to consider they don't have no mass. They do have a mass, but it's so unbelievably small. I tell my chemistry students, just consider no mass. So definitely for you, that's good enough. Protons and neutrons are located in the nucleus, and then the electrons are orbiting around the nucleus. Okay? There's 2 numbers that you need to know. One is the atomic number. The atomic number of an element is the number of protons. And that's like an ID number. Okay? You are identified by numbers, don't you? Haven't you ever had to put your social security number or your driver's license number? Why? Because that number represents you. If you know the atomic number, look for instance carbon. It has 6 protons, 6 neutrons, 6 electrons. Because they're neutral. You have to have the same number of protons and electrons. Because you have 6 protons, the atomic number, that's actually represented by C, is 6. Notice that we look at the number of protons because we're not going to get too much into this, but we will talk a little bit about how atoms gain electrons, lose electrons, share electrons. So you cannot use electron, the number of electrons as a definition. The number of protons does not change. So that is atomic number. The mass number pretty much gives you an idea how much does the atom weigh. We said the protons and the neutrons have mass, but the electrons really no. So we can say that the number of protons plus the number of neutrons, that's the mass number. The mass number represented usually with A. You have 6 protons plus 6 neutrons, so that's 12. The periodic table shows you all of the known elements, and this is an old periodic table because these ones in here, they have been classified now. But you have columns and rows, and they give you very important information about the elements, how they interact with each other, about their properties. Basically, to summarize everything for you, elements that are in the same column, they're going to have very similar properties. Okay? But you can make a very, very good estimate of how a particular element is going to behave just by looking at the position in the periodic table. And most periodic tables have a key that explains what all the different things in there are. We're not going to worry about this. Still is biology, right? Isotopes are very important in biology. It's the same element, but they have different number of neutrons, which means the atomic number changes. A very good example, because we use it a lot in biology, is carbon-12 and carbon-14. They both are carbon, so they both have 6 protons, or they wouldn't be carbon. But one has 6 neutrons, so the mass number is 12. The one has 8 neutrons, so that's 14. Why did I use this particular example? Because the age of many remains, as long as they are less than 50,000 years old, are determined by using carbon dating. And we'll talk a little bit more about carbon dating when we talk about evolution, because there is some problem with how people use the technique. But you get the idea. 2 atoms, the same number of protons, so they're the same element, the same number of neutrons, they have different mass. Those are isotopes. Okay? Some isotopes are very unstable, especially when you get into bigger atoms, and they release energy to become stable, so we call them radioactive isotopes, radioisotopes too. Very useful in research, medicine, you name it. The electrons are in orbits or layers around the nucleus. We call them shells, and you can have up to 7 different shells in there. The outermost shell is called the valence shell, and that's the one that matters because these are the chemically active electrons. The other electrons are just there because you have to fill, beginning with lowest energy, you fill number 1, and if there's still electrons, you fill number 2, and you keep filling until you run out of electrons. So all of the layers below the outermost, all they're doing is kind of holding everything together. The electrons in the valence shell, they're called valence electrons, those are the ones that react. And a very important rule in chemistry is called the octet rule, the rule of 8, says that many atoms, and they tell you, don't worry about the ones that are filling the first shell because it's very small and it can only hold 2 electrons, but many atoms want to have 8 electrons in the valence shell. There are a few really big atoms that can have more than 8, but this is the common rule, and as far as you're concerned, that's all you're going to be worried about. Okay? So when you have an element that the valence shell is not full, it's going to want to fill it. We said they want to have 8 electrons. So those are reactive elements. They want to do whatever. They're going to gain electrons, they're going to lose electrons, they're going to share electrons, they're going to do whatever they need to do to get 8 electrons. Because that's more stable. But if you have an element that already has a full outer shell, that's an inert element. Look for instance at sodium. In the outermost shell, it has 1 electron. Sodium could gain 7 electrons or lose this one. It's easy to lose this one because it's only 1. Because the shell immediately below is already full. So sodium minus 1 electron is stable because the outermost shell is full. Look at chlorine. Chlorine has 7 electrons. So the easiest thing is to gain 1 more electron, so it has 8. And now chlorine is going to have an extra electron. But we have in here, I believe this is neon. Yes, 10. Yep, was right, neon. The outermost shell is full, it has 8 electrons. It already has 8 electrons, it's not going to do anything, that's why it's inert. So, sodium and chlorine, they're going to react, pass an electron from one to the other, they're reactive elements. Neon, no, it's happy. Just leave me alone, I'm fine. Because some elements don't have complete outer shells, they're going to form chemical bonds in order to fill the outer shells. But those chemical bonds are going to hold them together, so you're going to form molecules. Yes, they become more stable, but now instead of individual atoms, you get molecules. And there's three types of chemical bonding. Well, I'm a chemist too, and this kind of hurts. There's ionic bonds, there's covalent bonds, hydrogen bonds. I hate to classify them as a separate kind of bond. Well, that's most biology books classify them as a separate, but it's a type of covalent, okay? You say whatever your textbook says. Like say, I happen to be a biologist and a chemist, and I hate to call hydrogen bonds separate, but like say many biology books do that. That's fine. So, what is an ion? An ion is a charged atom. Usually, the number of protons equals the number of electrons. Protons are positive, you have the same number of electrons, and your atom is neutral. But if the atom gains or loses electrons, like we saw sodium and chlorine doing in there, then they become charged. When the number of protons does not equal the number of electrons, there's going to be too many positive charges or too many negative charges. So you get an ion instead of an ion. So we're going to be transferring electrons from the valence shell. If you gain electrons, one or more, then you're going to have more negative charges. That's called an anion. If you lose electrons, you get positive charges, so you get a cation. That's the example we saw in here. Let me go back in there. Sodium lost an electron, became sodium plus 1. So that's a cation. I'm not going to let me write at the edge. Chlorine gained an electron, so it's an anion because it got a negative charge. Okay? By the way, if you had difficulty remembering which one is which, that was a chemistry student, but he wrote an exam. Cats are positively, and he spelled it like that on purpose, because he was talking about cats, positively great. Silly, yeah, but cats, positive. That's a good way to remember cations are the positive ones. But anyhow, you have a positive ion, you have a negative ion, opposite charges attract each other, so that forms an ionic bond. Going back to the example, when you have this ion attacking this ion, you end up with sodium chloride, table salt, and that's an ionic bond that was forming there. Here's just the same example. Sorry, I didn't realize I have been going back. But you have sodium losing an electron, becoming sodium plus 1. Chlorine gaining an electron, becomes chlorine minus 1. They attract each other. Notice that you have to have always one atom willing to lose electrons and one atom willing to gain electrons. You don't just throw electrons out in the trash because you don't want them. You don't get them out of your kitchen drawer. You always need to have both ions. On the other hand, covalent bonds are formed by sharing. Sometimes some atoms, they don't know what to do, or they don't care. Okay, let me give you a couple of examples. Carbon has 4 valence electrons in the outermost shell. Since we've been doing it with a circle. So you ask carbon, what would you rather do, gain 4 or lose 4? And carbon says, I don't know. When you're having 1 versus 7, it's very easy to choose. When it's 4 versus 4, I don't care. Well, let me give you another example. You have maybe, well, let me have oxygen. Oxygen has 6. Okay, 1, 2, 3, 4, 5, 6. And we have nitrogen because we know the form, and in the outermost shell, nitrogen has 5. So oxygen comes and says, hey, nitrogen, give me 2 electrons so I can fill my outermost shell. And nitrogen says, you crazy or what, man? I need electrons. I'm not going to give you electrons. They're going to argue. Neither one of them wants to give up electrons. Eventually, carbon, oxygen, nitrogen will realize that sharing electrons is the solution. Because the electrons that are shared are considered to belong to both of the atoms, so they both fill the outermost shell, they both become more stable, and they're happy. Now, when you're sharing something with someone, sometimes it works, sometimes maybe it doesn't work quite as well. Two atoms that are equal are going to share equally. So we call that a non-polar covalent bond because the electrons, let me give you an example. You have hydrogen, has one electron, and hydrogen. So they share, and because hydrogen and hydrogen are the same, they're going to pull on the electrons with equal strength. So the electrons are split 50-50. The charges are non-polarized, so we call it non-polar. Some people call it pure covalent. Some people skip the non-polar and just call it covalent bond. Okay? But let's imagine one of the atoms is stronger than the other one. I have hydrogen, one electron. I have chlorine that has 7. So I think I put one too many. They're sharing a pair of electrons, but chlorine is stronger. So instead of being a 50-50 distribution, it can be a 40-60 or maybe a 30-70. The charges are moved towards the chlorine. They're polarized, so we call this a polar covalent bond. Here you have some examples. In the molecule of water, oxygen pulls on the electrons. It's a polar covalent bond. So since oxygen attracts electrons towards himself, he gets a partial negative charge. It's a very, very small charge, okay? It's not even one charge. But hydrogen has the electron less than its fair share, so it has a small positive charge. These teeny charges, like I said, they're not even a full atomic charge. They're so important. We're going to see that all of the properties of water and water is necessary for life can be explained by the fact that water is a polar molecule. The charges are polarized. Teeny charges you can imagine, unbelievably important. Okay? When the atoms are identical, like two oxygens, or they're very similar in affinity for the electrons, like carbon and hydrogen, you get non-polar covalent bonds. Like I say, hydrogen bonds are really a form of polar covalent bonds. That's why I had to classify them as different. But they include the hydrogen. One of the atoms is going to be a hydrogen. Okay? And the other atom has to have a very strong attraction. Let me not use terms of electronegativity. I don't mean to confuse you. But it's polar. And one of the atoms is hydrogen. So you're going to have a slight positive charge over the hydrogen and a slight negative charge over the other one. So those charges in two separate molecules are going to be attracted to each other. It's a very, very weak attraction because those are teeny charges, but that's what we call a hydrogen bond. And it will be easy to understand. They have an example. We said oxygen is slightly negative, hydrogen is slightly positive. So the slightly positive is going to be attracted to the slightly negative. This is slightly positive, it's going to be attracted to slightly negative. So you see how you form these hydrogen bonds. They're extremely weak, but they're so common that they become very important. I remember I think 6 or 7 years old. My mama took me to a circus, and there was a strong man, and he could get the Madrid phone book and tear it in half in front of you. I went home thinking, I want to do that. You're talking about a really big phone book. There was several million people living in Madrid then. And I got the white pages and I tried to tear them, and my mother called me, my mama smiled, left. And I had a great idea. I cannot break all of the pages at once, but I can break one at a time. When my mother called me, I had gone through probably 1/4 of the phone book. What I'm trying to say is that just like one page is very weak, but the whole phone book is very strong, one hydrogen bond is very weak, but when you have millions of them, they become very strong. And think about water, how many molecules you have. There's no word for the number of molecules. We're going beyond trillions, quadrillions, something like that in a very small amount of water. So they become extremely important. Hydrogen bonds are going to be responsible for the shape of big important molecules in biology. They're unbelievably important. Not because they're strong, but because there's so many of them. So I want to talk about the properties of water because water is essential for life. And these properties are the reason why water is essential for life. So first let's mention them, then we'll look at each one. Water is a polar molecule, water stabilizes temperature, water expands when it freezes, water is a very good solvent, and water is cohesive and adhesive. So let's look at each one of them. We already said that water is polar. We said the hydrogen, oxygen, hydrogen. The oxygen has a little negative charge. Every hydrogen has a little positive charge. Okay? So when a substance can form hydrogen bonds with water, then it dissolves. And we call that hydrophilic. If you think about a sugar has lots of, it's a big molecule, but has oxygen and hydrogen. So this is going to form a hydrogen bond with a water molecule. Okay? That's a hydrophilic molecule. Philic means friend. He likes water. But whenever you can form hydrogen bonds, because it's a non-polar substance, then they don't dissolve. They're hydrophobic. And they have an example when you put oil in water, what happens? It makes little bubbles, little micelles, but you can stir as much as you want to, and the moment you let it sit, they separate again. Water and oil don't mix, right? Phobic means that hates. These are molecules that hate water. Their property is stabilizing temperature. When you go out, and it's late July when I'm preparing this, upper 90s right now, 90% humidity, miserable outside. The water stabilizes the temperature. If I step out, my body temperature is not going to go up to the environmental temperature in there. Why? Because of two properties of water. It has a high heat capacity, means, and that's caused by the hydrogen bonds. The hydrogen bonds absorb heat without the temperature of the water going up. We're not going to get to the details. Basically, you're talking about breaking and reforming. Don't worry about the chemistry. Just take it as hydrogen bonds absorb heat. So the temperature of the water rises and falls very slowly, and that allows an organism to keep its normal temperature. It's kind of like when you go to the beach, it tends to be less hot during the day, less cool at night, because of the modern effect of the water. Also, sweating helps you cool, but it's not sweating, it's actually the sweat evaporate. Water has a very high heat of vaporization, meaning for water to evaporate, it takes a lot of heat. Your sweat has to evaporate, and where does it take the heat from? From your body. So that's how you cool off. If you live in South Carolina or any place with high humidity, you know you can go out in the summertime and you're drenched with sweat and you're still hot. Why? Because the humidity is so high, the sweat does not evaporate, so you don't cool off. So sweating does not cool you off. The evaporation of the sweat cools you off. And both the high heat of vaporization and high heat capacity are linked to the hydrogen bonds. If you want to know more, I would recommend you take chemistry. Serious. Water expands when it freezes. Most things contract. You've heard about it. When something gets colder, it contracts. When it gets warmer, it expands. But when it's reaching freezing temperature, water expands. That's why in the winter, if it's very, very cold, you better put antifreeze in your car. You better let the water run, because if the water freezes in your radiator or in the pipes in your house, what happens? They burst. The ice expands and it can burst pipes. The reason the water expands when it freezes, the hydrogen bonds. It forms a lattice that expands. Okay, I understand that. But other than making sure I don't burst the pipes in my house, why is that important? Because you have the same amount of water on a bigger volume, the density is lower. Density is mass divided by volume. If the mass does not change, but the volume increases, the density decreases. So the ice floats. Why is that important for life? Well, imagine you're a little fish in a pond and start getting cold. Ice floats, gets on the top. Because it gets on the top, it actually works as a blanket. It keeps the rest of the world from freezing. I'm serious. It's very easy to get a thin layer of ice, but then it gets real hard to get thick ice. If you ever try to go ice skating, you know that. I lived 4 years in Washington, D.C. I don't know why. I daydream, because I used to go ice skating in Spain. And all of a sudden, the idea of ice skating on a river is sounded so much fun than going to an ice skating rink. And what could be more American than the Potomac River? So my first winter, I asked my mama for my skates. My mama said, you can buy new ones. It's too expensive to ship them. But every evening, I checked the weather report because they gave you the thickness of the ice. And they explained when the ice gets to a certain thickness, then the parks department will open the river for ice skating. He never got sick enough. Or the next winter, or the next one. I was 4 winters. I was never able to go ice skating because the ice makes it harder for the insulated water below, makes it harder to freeze. So this little fish is cold, but can survive. Now, if ice did not float, let's imagine the ice from at the bottom. It's not protecting, so the rest of the world starts freezing. The whole pond would freeze solid. What happens to the fish? It would die. So ice flowing is very important to maintain life in the winter. Water is a very good solvent because it's polar. We said that polar molecules are going to form hydrogen bonds with water and they can dissolve. The same thing whenever you have ionic compounds. Okay, table salt. We say it's from chloride ions and sodium ions because they have charges. Remember, this is the chloride ion that's negative. You cannot see very well, and this is the sodium ion that is positive. So the world surrounds it. If it's the positive ion, the oxygen that's negative is facing it. If it's the negative ion, then it's going to be the hydrogens that are facing. The opposite charges are attracting each other. So you form a sphere of hydration. These two ions that were holding on to each other, now the water molecule gets in between. And when they're surrounded by water molecules, they cannot attract each other. So they separate, they drift away, they dissolve. That's why water, being a polar molecule, allows it to dissolve many different things. Everything except for non-polar molecules will dissolve. So water dissolves many substances and it forms a solution. Whatever you're dissolving is called a solute, and we already mentioned that water will be the solvent. Those are terms we're going to be using all the time. Water is cohesive and adhesive. I don't know when I'm typing why. There's a difference between those two terms. Water molecules stick to each other because of hydrogen bonding. Those are identical molecules getting together, so that is cohesion. But water molecules can also adhere to any polar surface, like a paper towel. Paper towel is made of cellulose. It has lots of hydroxide groups. They are going to form polar bonds with the water. Okay? So when the water sticks to a different molecule, two different molecules are attracted to each other, forming hydrogen bonds, then we call that adhesion. That allows for water to be a very good transport system because things dissolve in the water and then they're transported. This example is, well, this is good, but the blood moves because the heart is beating. I understand that it's good that the materials dissolve in the water, but let me give you a better example than this one. Think on a big tree, the biggest tree you can think of, and it has roots underground. The water comes into the roots, but it has to go all the way to the leaves. You're going to see that water is necessary for photosynthesis. And then, once photosynthesis has taken place and the tree has made glucose, it has to be distributed throughout the whole tree. But the tree doesn't have a heart to pump the lymph. How does the water move through the tree? An example of adhesion and cohesion. You have very narrow tubes. The water sticks to the tubes and sticks to each other, so that pulls, and that pull is strong enough actually to make the water go all the way from the tip of the root to the top of the tree. Okay? Also, adhesion and cohesion cause another property of water that's called the surface tension. It's like water had a very thin skin, very, very thin, but it's good enough for some insects to walk on the surface of the water. And they can use that either go someplace, to go get something, find something to eat. It's very important for certain insects to be able to walk on the water. Let me give you an example how strong the surface tension is. If you're very careful, you can put a needle on top of a glass of water, and if you put it right on the surface tension will hold it in there. That's not a steel needle. It's not hollow. It should sink. And in fact, if you're not very, very careful, it will sink. You have to put it right on the surface. But the surface tension is holding, that skin is holding the needle in there. Why? Because you have water molecules that are attracting each other, but the ones on the surface, you have forces attracting it to the ones to the right, to the left, below, but there's nothing pulling upwards, so that will cause it a little skin to form in here. And if you look carefully at the picture, you can see that actually the surface of the water has a little indentation with the needles in there. Okay, so needle floats. But can you prove to me that it's due to hydrogen bonding? Yeah. Add a drop of liquid soap. Soap breaks the hydrogen bonds. You add a drop of soap in there, and the needle sinks instantly. You can try it at home. It's amazing. I used to do this at a demonstration in class. It was real fun. Another topic that's very important in chemistry, and we're getting close to the end, I promise, is acids, bases, and pH. To make it simple, an acid is any molecule that releases hydrogen atoms when you dissolve it in water. So this hydrochloric acid, when you dissolve it in water, a proton separates. A base, when you dissolve it in water, it releases hydroxide ions. So sodium hydroxide, that's Drano, breaks into sodium ion and hydroxide ion. There's a whole lot more than this, and they're based on hydroxide. Once again, if you want to know more, that'll be really a topic to discuss in chemistry. But remember, I can tutor chemistry too. Okay? The problem is the numbers that we use to reflect acidity, the concentration of hydroxide, the concentration of hydrogen, is so small that chemists came up with a scale that we call the pH scale. It ranges from 0 to 14. I'm not going to get into how you calculate the pH or something like that. That's chemistry. I just want you to know that when you have a pH of 7, that's neutral because you have the same number of protons and hydroxides. If you have more protons, you have a pH that's less than 7, and you have an acid, and the smaller the number, the stronger the acid. If the pH is above 7, it's a base, means you have more hydroxides, and again, the higher the pH, the more basic it is. So I have some examples in here. Distilled water is neutral. Urine is slightly acidic. Juices, many tomato juice, orange juice, lemon juice, As in your stomach, remember we talked about the cells that make hydrochloric acid? Hydrochloric acid has a pH of about 1. Examples of basic things that you may be familiar with, baking soda. Baking soda used to be used as an antacid. The only problem, it works real good, but it tasted real nasty. And if you have high blood pressure, it's not good for you. So they came up with milk of magnesia. Bleach that you add to your clothes is a very strong base. That's what cleans your clothes. Okay? When we talk about homeostasis, we say that's very important to maintain the internal environment, and acidity is one of them. So you have buffers. Buffers absorb any excess prons or excess hydroxides, so they keep the pH into a very narrow range. Okay? So a very common buffer system involves carbonic acid, carbon dioxide, and bicarbonate. I don't know if you can read it in there, so let me write in here. But carbon dioxide, when it dissolves in water, and this is an equilibrium, meaning the reaction can go in both directions, forms carbonic acid. Carbonic acid is a very weak acid, so it's going to dissociate into prons and bicarbonate. And all of this takes place in the blood. Okay? What happens if your blood is too acidic? You want to get rid of some of these prons because it's too acidic. How do you get it too acidic? You have to displace all these equilibriums towards the left. If you remove carbon dioxide, then the blood becomes less acidic. And your body automatically makes you breathe faster and deeper, so you get rid of more carbon dioxide. What happens if your blood is a little bit too basic? You're diabetic, you're being very careful with your diet, there's a chance that your blood may turn a little bit too basic. If you slow down your breathing, you accumulate carbon dioxide, so the equilibrium displaces to the right, you produce more protons, and you lower the pH. That's what a buffer does. It maintains a pH constant within a very narrow range. This particular example, it works only with prons, but there's buffers that will do either prons or hydroxides. Okay? And by the way, this is not the only buffer in your body. You have several buffers. This is probably the easiest to discuss. Okay, so once again, if you'd like to work with me one-on-one, if you want to practice with any of my worksheets or any of my tables to summarize chapters, if you want to study for an exam, there's a link to my Poisson Turing profile in the video description. Make an appointment, and I'll be glad to see you.